I would like to invite to the stage Mr. Sushant, and please, Sushant, give your talk.
All right, thank you. Thanks for having me. So yeah, really excited about talking about how we built our distributed fallback at Lyft. So that's going to be my main focus about why and how we built the distributed fallback. But I'm also going to be talking about some interesting tools and processes that we have at Lyft that help improve the resiliency of our systems. So even if you're not planning on building a distributed fallback or any sort of fallback for your stack, I'm hoping you'll get some takeaways, you'll get some inspiration for other things that you can do to improve the reliability of your services. So a little bit about me. I started as a full stack developer. I've built web, desktop, and iOS applications in the past. So I like thinking about products or features end to end and designing them end to end. I later moved to more of a backend role, worked on a few products, and then when Kubernetes started becoming popular, I was interested in that, so I joined infrastructure teams and helped build Kubernetes stack at a few companies. And then I moved back to more of a backend product developer role. In general, I'm interested in software architecture and distributed systems problems. So I like drawing boxes and lines, as you'll see in this talk. And I was also excited when I found out about the Amazon's Builders Library, which is a bunch of articles on software architecture, distributed systems, reliability. So I'll be referencing those in my talk a lot. And yeah, also excited about one of the talks we have on AutoMerge, which talks about CRDTs or conflict-free replicated data types. So interested in those sort of things as well when it comes to distributed systems. I've been at Lyft for a little over 3.5 years. And as I mentioned, I started on the infrastructure team and have now moved to a product team working on the back end. And this talk will focus mostly on my experience of working in this particular backend team. So Lyft, if you're not aware, is a single smart app to get around your city. Right now, we have rideshare options with everything from shared rides to extra large vehicles. We also have bikes, scooters, and transit information within the app. It's currently available to 95% of the population in the United States and a few select cities in Canada as well. And I work on the purchase flow team at Lyft, which is responsible for showing users all the relevant transportation options. So when users enter their destination and tell us where they are starting from, where they want to go, in the backend, we fetch all the options that are available in that particular market, available to that user. And then in real time, we figure out the price and the pickup and arrival estimates for those options, which you'll see on the right here. So once I've selected destination, all these options that you see are what we call offers. And the screen that you see here, we call it the offer selector, which has all the price and time information. So as you can imagine, this is a complex distributed system in the backend. All the requests from our apps come into our backend system or enter our backend system via a gateway service, which is responsible for content negotiation. So our apps can send us requests that are JSON over HTTP or protobuf over HTTP. But most of our backend systems now are protobuf over gRPC. So that translation is handled in the gateway. It's also responsible for basic authentication and authorization and some request validation. So the gateway is going to send all the validated requests over to the personalization system or personalization service, which is going to maintain the session state. So it's going to start a session for the user in the backend, persist that in a database, and then call other upstream services. We also have a geospatial configuration, which is a database and a release pipeline for that configuration. And so this is where we configure all the products or all the transportation options that are available. So based on the location of the user and based on where they want to go, certain products might be available in that particular market or for their particular trip. So this is a static configuration, but then we apply additional filters and additional business rules on them in the product generation service, which is going to return that list of products to the offer generation service, which is then going to get price and time estimates for all of those options, build those offers, and then send them to the personalization layer, which is going to group similar kind of options, which is going to rank them and personalize them for the user, and then send them back to the gateway. So as you see here, there are a lot of moving parts. We deploy multiple times a day to each of these services when we are adding features, updating features. So there's a lot of risk involved. There's always a risk that we're going to introduce some sort of bug which can take our system down. And this did in fact happen a couple of times last year, where we saw outages that lasted a few minutes. And an outage in our stack or our system typically means that the users see a blank offer selector. So they don't see any offers, so they can't request any rides, and they can't make any progress within the app. And because users are not able to request rides, that means drivers on our platform also cannot service any rides, so they can't make any money on the platform. And so if an outage like this happens, we also need to spend some time responding to support tickets, contacting users who were affected, and try and compensate them for the bad experience. So generally results in a loss of productivity as well. So we were wondering if we could prevent such a scenario, whether we could build a fallback that would help us in these situations. And let our users, continue making progress within the app. So let's talk about what a fallback is. A fallback is an alternate mode of operation that you may use in an emergency situation, in a certain special case, let's say. So let's say you have a system, a simple system that which can be a CRUD app. So whenever a request comes in, when you want to create a new record, you write it to a database, but you also write it to a cache, so that if there is a read request for the same record, then you can potentially serve it from the cache without going to the database. So if your read volume is significantly higher than your write volume, then you basically don't overwhelm the database for read requests. And you can get all those, you can query the cache for all the read operations. So that can be the normal mode of operation. But what happens if the cache suddenly becomes unavailable? So in that case, you might build a fallback mode in your application, which then makes all the read requests to your database instead of the cache. So this is a fairly common design. We see this a lot in production systems. And while it seems fairly simple, fairly straightforward, there can be issues with this. So one is that these scenarios can be hard to simulate and test. So maybe your cache becomes unavailable only when you see a sudden spike in traffic. So you might want to simulate that scenario in perhaps your staging environment. But you might have to consider other cases as well. So what happens if certain reads from certain paths, certain nodes fail, but some of them succeed. Does that lead to inconsistencies within your application? Does that lead to an inconsistent state within your application? So it can be a little tricky to simulate all of that and to test all of this. At the same time, your fallback mode is only getting executed in certain special conditions, whereas your normal mode is being continuously exercised and you're continuously developing or adding code or adding features to your normal mode of operation. So there is a chance that the two modes start diverging. Maybe the contract starts diverging. You may forget to update the fallback mode with the changes that you've made in the normal mode. So the fallback mode in that situation can fail. Also, because it's not being exercised regularly, it may have certain bugs that only manifest themselves in certain situations. So if, for example, you hit two different kinds of failure conditions, then a certain bug may arise that you may not have thought about. The last point is that the fallback can, in fact, make your outage even worse. So if we go back to this example, if your cache becomes unavailable and if your nodes, if all of your nodes start reading from the database, then the read volume on the database also can spike and it can overwhelm the database. So if your database then becomes unavailable, then basically your whole system is unavailable and your fallback has made your outage even worse. So I've linked to one of the articles in the Amazon's Builders Library that talks about this in detail. It talks about, it gives you an example that they had in production, an outage that they saw, which we looked at right now, but a concrete example, and it tells you what you can do instead of building a fallback in your system. So we were aware of these pitfalls of building a fallback, but we still decided to, go ahead and try and build a fallback only for certain very emergency scenarios. And in general, we decided that we needed to improve the resiliency of our system. So we came up with a few things that we could consider, we could look at and build a fallback strategy with that. So we will be talking about all of these things in detail as we go through it. So the first thing that we tried to do was improve the reliability of the normal mode of operation. And the way we did that was we injected failures between the different components, as you see here. And we wanted to make sure that non-critical components do not affect the critical path of operation, do not cause our system to go down. So we wanted to make sure that each of the components here can handle failures in non-critical components. An interesting sidebar to this is basically fault injection testing. So we recently posted on our blog about the chaos experimentation framework that we open sourced. So it's a UI framework built on top of Envoy. And this is a screenshot from that system that lets us run fault injection tests. So as you can see in this example here, I can define a downstream cluster and the upstream cluster, which is going to be its dependency. And I can specify the percentage of requests in which I need to inject some sort of fault. The fault types can be abort, in which case we will return a certain HTTP status code. In this case, you can see it's 500. Or you can also inject latencies in your network. And And then, yeah, we can run this experiment in either staging or production and see how the downstream cluster performs when there's an issue with the upstream cluster. So another sidebar to this is that we run a service mesh internally, which is Envoy. So Envoy was started at Lyft and later open sourced. And yeah, we run basically an Envoy sidecar, which is process. So all the requests going out of your service and coming into your service go through the Envoy sidecar. So the sidecar on Kubernetes can be another container that's running right next to your service container in the same pod. So whenever we provision a new pod or a new instance of a service, the sidecar that's running for that service is going to register with the Envoy control plane. And then the control plane sends it updates about the other services that are running, the services that that particular Envoy sidecar might be interested in, based on the service configuration. So if we, again, look back at the fault injection testing, what this will do is, based on the configuration that we set here, it's going to send that to the Envoy control plane. And then the control plane can send that configuration to the individual sidecar for the upstream and downstream services. So that way we can just inject failures in the sidecar itself. So if we want to inject failures in service B, for example, this sidecar can simply return that particular HTTP status code that we have, or increase the latency of the responses that are coming back from service B. So we, for all of our service code, we basically initialize an Envoy client, and we can specify the timeout, the retry policy for all of the requests as well. So that simplifies a lot of things for us. And in this particular step where we wanted to improve the reliability of the normal mode, we basically looked at all of that. We looked at our timeout and retry configuration. The Envoy sidecar also helps with failover. So if we keep getting an error response from a particular pod, it can fail over to another pod or another instance of that service. And then again, in this step, we looked at our runbooks. We looked at all the metrics and observability or the dashboards that we had, and made sure we can mitigate issues quickly if any issues happen. Our runbooks are updated, and basically everything in the normal mode is can be as reliable as possible. And we continue to invest in this. So because of the web application now, it's very easy to run fault injection tests in our systems as well. So that has helped us improve the reliability of the normal mode. So after we did that, after we made sure, or after we had that principle where every component needs to be resilient to non-critical failures in its upstream, we could come up with a simple fallback design. And that was to build the fallback mode in the gateway service itself. And the reason for that was basically, the gateway service is does not have a lot of business code. It's basically handles all the API level responsibilities. It does not get updated that frequently compared to other services which have a lot of business code, which are still in active development. So there's always a potential for those services to fail. And if we build a fallback in those services, then we still are not protected against any issues. So it kind of made sense to build the fallback mode in the gateway. And because the gateway itself is going to have an Envoy client for the personalization service, we can write simple logic in the gateway service itself, which checks the status code that it gets back from its upstream component, and if it's HTTP 500 or higher, then we can trigger the fallback. And this also becomes easy to test. We can easily write unit tests for this case, so we can thoroughly test the triggering mechanism in this case. The other thing that I guess I forgot to mention was the geospatial configuration. The updates to those configurations are proactively pulled by all its clients. So if a service needs this geospatial configuration, we basically have agents agents within our application code that check for updates to the configuration. And if there are any updates, then they pull the latest version of that configuration. So this then means that the gateway service can return a fallback response without depending on any other component. So we can basically assume that if we get an error response back from the personalization layer, we can assume that nothing else is working as expected, and the gateway can itself build a fallback response and return it back to the client. And so this kind of technique or this principle was named static stability. Again, I've linked to an article from Amazon's builders library. So what this means is that the system can continue to operate, can continue to remain stable, even if any of its dependencies become unavailable. So in this case, whenever we spin up a node of the gateway service, it's going to proactively keep pulling updates from the geospatial configuration. So even if the configuration becomes, or this particular service becomes unavailable, it still has local data. It might not be the latest version of the configuration, but it can still build a fallback response and it can serve it to the client. Do note that in this case, if we were to provision another node of the gateway, then that would fail. So static stability also means that we need to over-provision the number of nodes for the gateway service so that we can handle traffic, certain traffic spikes in our system as well. And so we typically do that by reducing the number of resources allocated, but spinning up more number of Kubernetes pods for this. And Kubernetes does allow us to vertically scale the gateway nodes if required. The other thing that we did was we reused some of the code from the normal mode of operation. So once the gateway service has the product configuration that it requires to respond to the user's request, again, based on their location, it basically reuses the code that we use in the normal mode of operation. So the only difference in this case would be that it's working with a different set of products or a reduced set of products, whereas in the normal mode, we'll have richer data, we'll have more products that are available to that user. So this is just example code, but it demonstrates that we can reuse the same code that is run in normal mode. So this way, we get to exercise that code both in the normal and the fallback mode. We can test it thoroughly and reduces the chances of latent bugs in our code. And then we also run acceptance tests continuously in our system. So basically, what this chart is showing is that for a certain percentage of requests in our staging environment, the fallback mode is being executed. So this does not test the triggering mechanism, but this tests the fallback response. And how this helps us is basically once we return a fallback response that does not have upfront pricing information, the pricing system can also then test their fallback where they need to calculate their price based on the time and distance after the user trip is completed. So again, helps us test the fallback in different domains as well. And we do this using feature toggles, which basically allow modifying system behavior without changing code. So we recommend that any major or critical feature or a new integration basically be deployed behind a feature toggle. So that way we separate the deploy and the release step for a particular feature. So once you deploy that code, it will be inside your pod, but it will not necessarily execute until you turn on that toggle for that particular feature. We implement this configuration of feature toggles as a Git repository, which helps us with, so it's kind of simplifies the reviewing and observability of this system as well. So changing a feature toggle is basically opening a pull request. You can get your teammates to review it. And then if you need to look at what feature was enabled when, then you can also look at the Git history for it. And that things become easy that way. What's interesting is that we support a hierarchical configuration of these toggles. So we can have environment-specific overrides, or we can have geographical overrides as well. So when we try and fetch a value of a particular feature toggle, we can build context from the request that we are seeing. So if, or rather, based on the location of the user, the origin of the user, we can generate a geographical code. And if we have a feature toggle override for that particular geographical region or code, we get that particular value. If not, then we just return the default value for the toggle. So going back to this example, that's what we're using here. So this is an override in a staging environment and a particular location. So the green lines, if you can see them, are basically manual runs, and the yellow line is the continuous testing platform that is running the test continuously. And so the simulation platform basically exercises all critical endpoints in our backend, not just our domain, but the entire domain that's involved in the entire flow of the app. So when the user opens the app until the user gets dropped off to their location. So yeah, I've added an article on feature toggles, which goes into much more details about how you can implement them and different types of toggles that you can have. Then, you obviously need to thoroughly test the fallback end to end. So like I mentioned, we have exhaustive automated tests for testing the triggering mechanism. We have tests for testing that the fallback response that gets generated in the gateway is always valid. And then we can inject failures in our service mesh and manually test that it's getting triggered as expected. And then, as we looked at the continuous testing and the simulation platform, we can also continuously run them in our staging environments as well. And with every client or with every app release, we also run regression tests, automated and manual regression tests to ensure that the fallback continues to work with every build of our iOS and Android platform. And then finally, we also support disabling the fallback, again, with the feature toggles that we have. So if the fallback gets triggered and we notice that it's making the problem worse, it's affecting some other upstream service, then we do have a way of disabling the fallback. And I guess one thing I forgot to mention about the feature toggles or configuration system that we have is that we can deploy those changes within 2 minutes or so. So once we make that change and deploy it, we can disable a particular feature, or in this case, the fallback, in 2 minutes if we notice that it's making the problem worse. So finally, this is how the fallback looks in our system. This is how we implemented it. As you can see, it's a degraded experience. The users don't see the price or the time pickup and drop-off information. It's a reduced set of offers or transportation options. We can't show certain options that may be more dynamic, like a bike and scooter, which may not be available in that particular location. And we also don't personalize those offers. So we don't run some of the other complex logic that runs in other parts of our stack when we see an issue. So this does work as expected. The users can still request any of these, use any of these offers and request rights, and yeah, it continues to work. And this is an actual chart of where, this is an actual chart for when we did see issues and when the fallback was triggered. And so this is the number of rights that were requested using those fallback offers. So again, it goes to show that it is working as expected, and it continues to work as expected if there's an outage in our system or even an outage in our infrastructure. So yeah, we went through all of these, but just to recap, first, invest time in improving the reliability of the normal mode of operation. Then if you decide to still build a fallback, make sure the design is very simple. Try and reuse code that you would regularly exercise in your normal mode of operation. Still try and exercise the fallback mode as well in your staging environments, perhaps your production environments as well. Make sure you have enough automated tests. You can manually test the fallback, and then finally, still make sure that you can quickly disable the fallback if you think it's making the outage even worse. So yeah, that was my talk. Happy to answer any questions here, and you can also send me questions and feedback on my Twitter handle as well. Yeah, thank you.
Thank you very much. Thank you, Sushant. It was a very great talk. I enjoyed it at least a lot. And I see that there are already questions in the question and answer tab. So, but please be brave for all the audience. Let's give Sushant an applause. So I see you clapping. And then let's type in your questions. So let's see the first one. It would be István's question, István Fabian's question. Do you use a mechanism like circuit breaker? I don't know this mechanism, but
yes, again, that's configured. So circuit breakers would basically in the Envoy sidecar drop request if the number of connections to that particular sidecar are higher than your configured number of connections. So we do have that configuration in. We do configure that in the service mesh. And we can run redline tests, again, in the UI that I showed for the chaos experimentation platform. That UI also supports running redline tests, which is basically you send all the requests that are coming into one particular instance, and you can see how many requests it can handle, and you can provision your resources for that instance appropriately. So with that, you can also configure the max number of connections it can handle, and you can configure your circuit breaker settings that way as well. Yeah.
Mm-hmm. Thank you. Let's see the next one. Is not the gateway a single point of failure in the system?
Yeah, so that's why I've mentioned that this fallback is a best effort fallback. If the gateway fails or if the gateway is unavailable, then yeah, we can't recover. But so far, but yeah, I guess again, the point of having that in the gateway was that the gateway does not get updated that frequently. So far, there haven't been any issues, and we try to still maintain that principle of static stability. So if a gateway instance is running, then it does not depend on any other service. But if we have a significant outage with our cloud provider, then yeah, that may still fail. Yeah.
Okay, thank you. Next one, what SLA are you committed to?
So internally, we define SLOs, and we have different tiers for our services. So all the services that are in the critical path that are required for the app to work would be considered tier 0, and we have SLOs for them. So yeah, I guess an uptime of 4 nines and stuff like that. I don't remember the exact SLOs that we have, but yeah. Some of our services would be tier 0, and they need to have a stricter SLO than some other services that are not required in the critical path of the application.
Then another question from me, actually. In many cases, it is not recommended to use these distributed fallback strategies. So do you have any hint when to apply this method or when to not apply this method?
Yeah, basically depends on whether the fallback response that you send back is actually going to work for your system, for your users. Whether you're okay sending a partially degraded, whether you're okay presenting a partially degraded user experience to your users, and whether your users can still continue functioning, using your app in that case. So you can think of it as more of a business requirement, and whether you can, prevent business impact for your service, and whether it still makes. And then if you decide to still go ahead with that, then you need to make sure that you're testing it thoroughly, you're exercising that fallback regularly, and all of that. Yeah. Does that answer your question?
Yes. It's done. Actually, I'm working in telecommunication, and in many cases, we don't use the fallback in order to avoid additional load on the system, because it might be that sometimes it's just, the famous IT saying is that restarting works better in some cases. Yeah, okay.
Yeah, so as long as your fallback, as long as your design is simple, it does not take down any other parts of your system, and you can design it that way, and it makes sense for users, then you can.
Yeah, that's a very important point, not to bring additional load, which is probably even making the situation worse, right? It's an important aspect of consideration. One thing I would like to present you is a small gift from the organizers of the conference. It's you, even if you don't recognize. You will get it shipped via mail, so you will receive it soon, and I hope you will enjoy your tea or coffee out of it at your convenience.
Awesome. Yeah. Looking forward to drinking my coffee from that.
Yeah, thank you very much once again for your presentation. Before we are closing, because you were the last presenter of the day, I would like to just very briefly mention once again that the day is not ended. So there are links pasted into the chat. You can join to this virtual escape room. You can join a virtual Budapest tour. And you can also go to this interactive networking platform, WonderMe, which is also shared in the, I have never used this platform, so I will try it myself as well. But it's also pasted in the chat, so you can go there and then you can start some mingling. Hopefully next year we can show you Budapest in a much lively way in person, but this year we are sticking with this. So thank you very much once again for your presentation, and thank you very much for all of you who were listening and contributing. Don't forget to rate the presentations, don't forget to comment, and please feel free to contact each other anytime and discuss the relevant questions. It was a pleasure to listen to all these group presentations during the day. And with this, I would like to close today's event on this stage. And as I said, it continues on the virtual tour and in this virtual escape room and in the breakout sessions. By the way, you can also use Hopin to create session, invite people there, and create some own sessions there. So there's a lot of opportunities for collaboration to be found out. Thank you very much. I say goodbye.